So we all think we know energy, right?
Yeah, pretty much. It's, the capacity to do work power lines.
Right. Or even Einstein's famous EMCI toy. Seems totally fundamental, concrete.
Definitely.
But what if that whole understanding, that sort of bedrock idea, completely breaks down when we look at gravity, like with our best theory?
Yeah, that's a deeply weird situation. It really forces physicists to ask, well, what is energy fundamentally?
Exactly. And that profound weirdness, that's what we're diving into today.
A deep dive into what energy really means, or maybe what it doesn't mean in the way we expect it to inside general relativity.
We're digging into insights from this really fascinating article called Why Energy in General Relativity is So Weird.
Yeah, it lays out the problems very clearly.
So our mission here is basically to pull out the core challenges the article talks about, look at some history, the attempts to fix this.
And some of the, frankly, bizarre paradoxes that come up.
Yeah, think of this as your shortcut to getting your head around this pretty peculiar corner of theoretical physics.
And the central paradox the article really hammers this home is that even though we use the word energy all the time,
Constantly.
defining it in a way that's like universal and conserved across the board in GR's curvy spacetime, it's incredibly hard.
Sometimes it feels impossible, doesn't it? Like energy just doesn't play by the rules we thought it did.
It really doesn't.
Okay, so let's unpack that. Why? Why is it so difficult? What's going on in general relativity that messes up our nice, neat ideas about energy conservation that work everywhere else?
Well, what's fascinating and kind of ironic is that the problem really stems from GR's biggest strength.
How so?
Our usual definitions of energy, they just aren't enough because GR doesn't treat gravity as just another force acting on a fixed background, like a stage.
Right, it says gravity is the curvature of space-time itself.
Exactly. And because space-time isn't static, it's dynamic, it participates,
Hmm.
the old rules about energy just, well, they fall apart.
And the source material we looked at, it points to GR's two big foundational ideas as being kind of the culprits here, right? General covariance and the equivalence principle.
That's right. General covariance, that's the principle that physics laws should look the same no matter how you set up your coordinates, your grid lines. It's about finding truths that aren't just artifacts of your perspective.
Okay. And the equivalence principle.
That's the idea that locally, like in a small enough region, you can't tell the difference between being in a gravitational field and just accelerating.
Okay, so these two powerful ideas, they actually make it harder to define energy. That seems counterintuitive.
It does, but it's because our usual ways of defining energy often rely on having some fixed background or special symmetries that are tied to specific coordinate systems. General covariance wants us to get rid of that coordinate dependence.
So the very elegance of GR makes finding a universal energy concept tricky.
Precisely.
So physicists obviously didn't just throw up their hands. They tried to find ways to, put energy conservation back into the picture. The article mentions Einstein himself had an early go at it.
Yeah, he did. Early on, he tried adding this extra mathematical bit to his equations, something called a pseudo-tensor.
A pseudo-tensor. What was that supposed to do?
The hope was that this term would represent the energy of the gravitational field itself. So if you added the matter energy and this gravitational pseudo-energy together, the total would be conserved globally.
Okay. Seems like a potential fix.
Yeah.
But the source makes it pretty clear this wasn't ideal.
No, not at all. It created a whole different kind of problem.
Which was?
Well, the name kind of gives it away, pseudo-tensor. It means it's not a real tensor. And the consequence of that is that its value, the amount of gravitational energy it represents, changes depending on the coordinate system you happen to choose.
Wait, so you change your graph paper, essentially.
Yeah.
And the amount of energy changes.
Exactly. You pick one coordinate system, you get one answer. You pick another mathematically equally valid one, you get a different answer.
That doesn't sound like a real physical thing. A physical property shouldn't just change because you described it differently.
Precisely. And that's why many physicists saw it as, well, a bit of a kludge, a workaround.
Yeah.
It felt like it violated the whole spirit of general covariance, that core idea that the physics shouldn't depend on your arbitrary coordinate choice. It felt like a step backward, really.
Okay, so the pseudo-tensor was a problematic workaround. Is there any situation in GR where energy can be properly defined, conserved, and, make sense?
Yes, there is. But it requires very specific circumstances. The source brings up killing vectors.
Killing vectors. Okay, what are they?
They basically represent continuous symmetries in spacetime. Think of it like if you can shift things in spacetime along a certain direction, like forward in time or rotationally, and the spacetime geometry looks exactly the same, that's a symmetry represented by a killing vector.
Right.
And if a spacetime has a particular kind of symmetry, specifically what's called a time-like killing vector, essentially, a symmetry related to time translation, then yes, you can define a conserved energy that's coordinate independent and mathematically elegant.
Ah, that sounds much better. So what's the catch? Why isn't this the universal answer?
The big catch, and the article really emphasizes this, is that most space-times we actually care about in the real universe, things like stars, galaxies collapsing, and crucially, our own expanding universe, they don't have these perfect time translation symmetries.
So the elegant solution only works where things are relatively simple and static.
Pretty much. The killing vector approach is beautiful, mathematically sound, but its applicability is limited, especially in the most dynamic and interesting cosmological scenarios where we'd really want a concept of total conserved energy.
Okay, this is where it gets really interesting then, because this isn't just abstract math trouble. The article points out how this pops up when we look at actual things like black holes or neutron stars.
Exactly. Let's take the Schwarzschild solution that describes the space-time around a simple, non-rotating black hole.
Okay.
That spacetime is highly symmetric. It has that time translation symmetry. So in that case, you can use the killing vector method to define its total mass, which is essentially its total energy, that you always see in the Schwarzschild metric. It's calculated precisely this way. It's a case where the symmetry approach works beautifully.
Right, so that works. But what about something less pristine, like a real physical neutron star? They're messy, they're dynamic.
And that's where the weirdness really bites. The source highlights this clearly. For something as concrete as a neutron star, the total energy you calculate can actually depend on the mathematical method you use to calculate it.
Wait, different methods give different energies for the same star?
Yes. The article specifically mentions comparing the ADM mass and the Missner-Sharp mass. These are different mathematically valid ways to try and define the total mass energy of a gravitating system.
And they don't agree.
Often, they give different numerical results for the same neutron star. Yet both methods have strong arguments behind them.
That's deeply strange.
It is. The insight here is that the value you get for the star's energy seems to depend on how you sort of mathematically draw the boundary or which definition you prioritize. It forces you to ask, which number is the real energy?
Or is energy just not uniquely defined in these situations? Is it inherently ambiguous or context-dependent in GR once you lose that perfect symmetry?
That seems to be the implication. It gets really unsettling.
And if we zoom out even further to the scale of the entire universe,
Right.
cosmology, the problem gets even more pronounced, right?
Absolutely. The source is quite clear on this. In an expanding universe like the one we live in, there is simply no globally conserved energy in the standard sense.
No conserved energy for the whole universe.
Nope. The idea that the total amount of energy stays constant just doesn't hold true when the space-time itself is stretching and evolving dynamically.
So where does the energy go? Or where does new energy come from as space expands? Does GR even give an answer?
That's the crux of the problem. Our usual framework of conserved energy doesn't provide a straightforward answer there. But interestingly, the article mentions that physicists can derive a different quantity in cosmology, let's call it S, like the source does, which is conserved.
Okay, a different conserved quantity, S. What's special about it?
What's really intriguing is its connection to thermodynamics. The source points out that this conserved S quantity acts very much like entropy in the first law of thermodynamics. You know, the one usually written like d dou u dollar equals TDAS.
Ah, okay, so energy E can change, but this S thing stays constant.
Exactly. And this formulation hints at something profound. Maybe, just maybe, in the grand scheme of cosmology, entropy is actually the more fundamental conserved quantity rather than energy itself.
Wow, okay, that's a huge conceptual shift, thinking of entropy as being more fundamental than energy.
It's a provocative idea that emerges from trying to make sense of conservation laws in an expanding universe.
What about gravitational waves? We see their effects. LIGO detects them. We see binary pulsars losing energy at exactly the rate predicted if they're radiating gravitational waves. That strongly implies these waves carry energy away, right?
Absolutely. The observational evidence is undeniable. Systems lose energy, and gravitational waves are the mechanism.
But does GR have trouble defining the energy in the waves themselves?
This is another one of those fascinating paradoxes the source digs into. While we know they carry energy away, if you try to use the standard, rigorously defined mathematical tools in GR, the fully covariant stress energy tensors that should describe energy density.
Yeah.
Gravitational waves appear to have zero local energy density.
Zero. But they're literally warping space-time. They must have energy.
Exactly the puzzle. It comes back to gravity being the curvature of spacetime, not a field in spacetime. Defining the energy of the curvature itself locally is tricky.
So how do physicists actually talk about the energy gravitational waves carry then, if the correct way says zero?
They use workarounds. They often resort to using those pseudo-tensors again, or they use averaged quantities over a region of spacetime, like the Isaacson tensor. These methods give sensible answers that match observations.
But they're approximations, or not fully rigorous within GR's framework.
Right. As the source notes, these are useful tools, but they are approximations or rely on averaging, and they don't really resolve the fundamental issue of defining gravitational energy density locally in a completely satisfactory, coordinate-independent way. The definition problem persists.
So if we try to sort of tie all this together, the core message from the source seems to be that there just isn't one single, universally agreed upon definition of energy in general relativity that does everything we want it to do.
Yeah, that's a fair summary. No single definition seems to satisfy all the criteria simultaneously. Being conserved everywhere, being independent of coordinates, and representing a clear physical quantity in all situations.
It feels like Einstein's masterpiece, GR, which works so well everywhere else, has this strange incompleteness when it comes to energy.
The article definitely leans that way. It suggests the framework seems incomplete on this specific but very fundamental point.
Does it mention where physicists think the solution might lie? Any ideas floating around?
Well, it touches on a few lines of thought. Some physicists wonder if maybe only the energy of matter and non-gravitational fields is truly definable in a universal sense, and the whole idea of localized gravitational energy is inherently problematic or maybe just not a meaningful local concept.
So maybe gravity's energy isn't like other energy.
Perhaps. Others think that getting a truly consistent picture might require going beyond GR itself, needing a deeper theory, perhaps a successful theory of quantum gravity, to fully resolve these ambiguities about energy at the fundamental level.
Right, the quantum gravity connection makes sense for deep puzzles.
Mm-hmm.
So for you listening, what does all this actually mean? I think it shows that even concepts we take for granted, concepts that feel really solid like energy, they get incredibly strange, really complex when we use general relativity to probe the universe at its deepest level.
It really challenges our basic intuitions about how reality works and how we even measure things within it.
Why is it so hard for GR to nail down energy? And the source, it leaves us with this really thought-provoking image, an analogy.
Oh, the mirage analogy.
Right. It suggests energy in GR is kind of like a mirage.
How so? Explain that a bit.
Well, it seems real. It seems solid and important. And in certain places, under specific conditions like that simple black hole spacetime, it looks consistent, well-defined.
Okay.
But the moment you try to pin it down universally or look closely in more complex situations like that neutron star or the expanding universe or inside gravitational waves, it becomes elusive.
Yeah, fuzzy.
Yeah, the definition gets fuzzy. Or it depends on how you look, your coordinate system, or which mathematical tool you use. Sometimes it even seems to morph into something else, like entropy, or its value changes, or it just seems to vanish locally.
Like a mirage shimmering and changing shape depending on how you view it.
Exactly. But here's the final kicker from the source.
It's a clue.
Yeah. This ambiguity, this difficulty in defining energy, it isn't necessarily just a flaw or a bug in the theory. It might actually be a clue, a hint from nature itself.
A clue about what, though?
Well, that's the question, isn't it? What deeper reality is physics pointing towards by making energy behave in this profoundly weird way within general relativity? That's the thought to maybe keep exploring.
Absolutely fascinating. Really makes you rethink something you thought was simple.
It really does. A true deep dive today, thanks to the source material that got us thinking about all this.